We now go from the west coast of Canada across the United States to the east coast, the southeast coast of the United States, where we find Mohamad Hussein. And he's going to talk also about dynamic pile testing. So, Mohamad, take it away.
Thank you, Gerald, and hello, everybody. Thank you, David. As Gerald mentioned, I will talk about dynamic pile testing, how that can save money. I will start with a little bit background and then go through a few case histories. So driven piles have been used since antiquity and have been mentioned in writings 2,500 years ago. In fact, we still have buildings that are hundreds of years old, founded on piles, still in service all over the world, as a matter of fact. These foundations are what made our cities possible, and as such, our civilization possible by allowing our cities to be built. Nowadays, driven piles are used to support all types of structures and all types of geotechnical conditions by supporting all types of load combinations to very, very high levels. The best reference I may suggest to you for the design and construction of driven piles would be this manual in 3 volumes from FHWA that can be downloaded for free from the internet. Driven piles can be categorized in a variety of ways, one of which is the materials, so that they consist of timber piles, steel piles, and concrete piles. They're often uniform, but not always. They can be made highly non-uniform in geometry and also in material properties to fit the conditions of the project. They are typically driven with impact hammers, and there are hundreds of hammer models to drive piles consisting of hydraulic hammers, air hammers, diesel hammers, etc. It has long been known by pile drivers intuitively that the more work it takes to drive a pile, the more the pile should be able to carry. So there's a relationship between the work and the goodness of the pile, something that in the late 19th century, Mr. Wellington expressed in a formula, since known as the energy formula, where he related the energy of the hammer to the resistance of the pile, and so presumably, therefore, its load-bearing capacity. Since then, many people have tried to improve in that approach. There are literally hundreds of such formulas based on the same principle, none of which really provide much improvement to the performance of the method. So in general, that is not generally recommended for use in today's practice. So let's look at what really happens when a hammer hits a pile. And one will find that when the hammer impacts the pile top, the whole pile is not sensed at once, but a portion of the pile knows that it was being impacted. As a matter of fact, one can approximate the length of pile that was impacted would equal to the weight of that pile length that is equal to the hammer weight. So therefore, the weight of the hammer dictates the length of the wave in the pile, and the drop height of the hammer dictates the intensity of the stress in that pile. So that's how the energy of the hammer weight and height and drop height gets transformed into the pile by wavelength and intensity. So that elastically compressed portion of the pile then travels down the pile length in a one-dimensional wave fashion, reflects from the end of the pile and comes back. So now we have stress waves going up and down the pile, initially from the hammer and reflected from the end of the pile and also from soil resistance effects. These stress waves travel at very high speeds, something like 15 or 16,000 feet per second. The use of that approach of wave mechanics was captured by a Mr. Smith, who was the chief engineer at the Raymond Company, who wrote a computer program often cited as the very first application of digital computers in civil engineering. Mr. Smith wrote a wave equation analysis program to follow these stress waves up and down the pile in numerical fashion in order to estimate the driving stresses on the pile and the load-bearing capacity. So that approach is called now the wave equation analysis of pile driving. And in fact, there is a wave equation. This is a wave equation, second-order differential wave equation that relates variables, energy, displacement, stress, etc., in the pile, that relates variables to time and distance from the pile top as it relates to the wave speed inside the pile. So that is a wave equation itself that Mr. Smith utilized with wave propagation to write the wave equation analysis program. Now, there are programs commercially available that use that approach to simulate the dynamics of pile driving. It's a very powerful, these are very powerful approach, and these programs are very good. However, being a simulation program using numerical analyses require assumptions. So one have to assume certain things and come up with results. Having said that, there are sources of error where these results can be off because of the uncertainty from the assumptions, such as hammer performance, cushion performance, soil pile interaction performance, etc. So there are sources of error where that simulation may not be exactly correct every time. Instead of assumptions and using numerical simulation analyses, we will talk about measurements. So now we'll go out to the field and perform measurements, analyze these measurements, and come up with these results needed for the pile driving. So a pile is typically driven to a certain depth and resistance to acquire enough load so it can carry the structure it's supposed to support. It will carry its portion of that load of that structure. So the best thing to do then is to drive the pile and know how much load it's supposed to carry and actually test it to that. So while we are driving the pile encounters pile driving dynamic resistance. What we want to know actually is its static load bearing capacity, because that is the value that is needed to support the structure. Static load testing, as David had mentioned in the previous presentation, can be performed in various ways. In this case, you can see using dead weight or reaction piles. But nevertheless, the idea is to statically load test the pile by incrementally loading it and then measuring the incremental corresponding movement of the pile, displacement of the pile. In this case, we see the pile top load versus movement. Of course, one can have instrumentation along the length of the pile as well, but more typically, the pile top load versus movement is what is being provided. So this is a typical static load test result. That's why we run a static load test. And I highlighted it in red because I will come back and revisit this same plot in a few more slides. So static load testing is great, and that's the best thing you can do actually. However, it has many limitations, and as far as time consumption, it takes a lot of time, expense, it can be very expensive, and also in way of application in certain situations that it just simply cannot be done. Not only that, but typically, as soon as the piles are driven, then everybody is very anxious to use them to build the superstructure, being a building or a bridge. So there's a very short amount of time, a very small window between the installation of the pile and its eventual use. So what we would like to do then is to see to come up with a relationship or to extract from the dynamic pile driving resistance the static pile load bearing capacity during installation, during the installation process itself. So let's try to think back a little bit. So that's a static load test. We need all of that weight to statically load test the pile with it. What if we were to think a little bit differently? If I was to take a small portion of that weight, put it in a guide, lift it up high enough and drop it in such a way that that process gives me the same load on the pile as all of that static load. So that is basically the difference between a static load test and a dynamic load test. As a matter of fact, none of this has to be done. It is being done automatically for free during the pile installation, and that is called the pile driving hammer. So the pile driving hammer is load testing the pile with every blow it uses to install the pile. So the installation process is the test of the pile. Now all we have to do is put some instrumentation on the pile and take measurements during pile driving, and that is what we call by a dynamic load test during installation. That is typically done in accordance with ASTM standard D4945. So dynamic testing, therefore, is nothing but measurements of the stress waves inside the pile. That is done by using typically two instruments, a strain transducer to measure the force in the pile, and accelerometer to measure the pile motion, its velocity and displacement. So now under each hammer blow, we're measuring the force in the pile with a strain transducer and the movement of the pile, its velocity from the accelerometer. That dynamic testing is typically done on site by physical presence of the testing engineer on site, or it can be done remotely by a site link type technology where the testing is done remotely from the site in a certain office. As a matter of fact, I love this picture. It shows an engineer actually performing a dynamic load test, sitting on an airplane going from somewhere to somewhere else. So this is typically the plot of one data from one blow. The red line is the pile top velocity, the pile top force, and the blue line is the pile top velocity during one blow. And what David showed earlier, he mentioned the wave up. So the bottom line is that the bottom plot, the black line is a wave down the pile, and the green line is a wave up the pile. I'll go in more detail in a moment about these plots and what they mean. The point being, each and every blow is a load test on the pile. In this case, it took 231 blows to drive this pile, some 12 feet. And this is a full record of the entire installation of this pile, showing pile driving stresses on the left side versus depth versus elevation, tip elevation. The hammer stroke height, this is a diesel hammer, so the stroke height varies. And on the right-hand side, we see the static load bearing capacity and the blow count versus depth. So this is a record of the entire installation process of this pile. The information contained in that record of installation can be used to evaluate the hammer performance, pile performance, and soil performance, soil resistance performance. The best way to perhaps assess the hammer system performance is by measuring the amount of energy that gets transferred into the pile. So that's transferred energy. If we compare the transferred energy to the potential energy or rated energy of the hammer, we see a very wide range that ranges anywhere from, let's say, 20 to 80% or something like that. The reason for that wide range is depending on the mechanical condition of the hammer and also the condition of the cushions in the hammer, or in the case of a concrete pile, the pile top plywood cushion. So all of these contribute into why that range can vary. At the same time, the data is used, the information, the dynamic test result information is used to evaluate the pile driving stresses in order to avoid damaging the piles during the installation process. There are two fundamental relationships that one has to be mindful of with this testing, dynamic testing. The first one is 2L/C. L is the pile length, and C is the stress wave speed inside the pile. And then the relationship between the two independently measured force and velocity. Force is measured with the strain transducer and velocity with the accelerometer. The two are independently measured, but related to each other by the pile impedance, which is Z. So 2L/C is used to time the records, because that is the 2L/C. It takes an amount of time, L/C, for the wave to travel from top to bottom of the pile, another L/C to go back. So the amount of time, 2L/C, then is an indication of the reflection from the pile toe. So that is one cycle of wave propagation, wave down and then up. The relationship between the independently measured force and velocity is related by the pile impedance, that itself is a function of the pile geometry and material properties. So impedance Z is equal to elastic modulus times area divided by the stress wave speed. If we work out the units, then I can scale or multiply the measured velocity in feet per second times that impedance. It comes to be in kips or force units. So now I can superimpose force and velocity already proportioned by impedance to look at the relationship between these two independently measured quantities. So when the hammer hits the pile top, as soon as the stress wave reaches the gauge locations, we see a great jump in the force and velocity of the pile. The force here is shown in a solid line and velocity in dotted line. The stress wave continues down the pile length, reflects from the pile toe and comes back up. So this is a signature. This is one data from that one blow. This is the result of one dynamic load test showing the pile top, force and velocity, time history, time record. That time history can be easily converted to distance, because the distance and the location and the time are related by the constant wave speed. So these are the measured data on the left-hand side, force and proportional velocity. And from that, we extract the wave down and the wave going up the pile. So now we know the wave going down the pile from the hammer and the wave going up the pile from the end of the pile and the soil resistance effects. So when the hammer hits the pile top, it generates a stress wave. So stress times area is force. So in a way, it forces the pile down into the ground. That movement of the pile activates soil resistance that itself sends back wave reflections. So now we have the waves going down the pile from the hammer and the waves going up the pile from the soil resistance, and they all get captured at the gauge location with the instrumentation constituting the dynamic load test. The ones on the left-hand side is data with no resistance. You'll notice that at the bottom of the pile, which is the right-hand side of the plot, showing the force in solid lines. So we have zero force at the pile bottom and very high velocity because we have no resistance. On the right-hand side, we see when we do have a lot of end bearing, that tends to increase the force and decrease the velocity. So when we have fixed end bearing, a lot of end bearing, the velocity is zero and the force is very high. Notice the force at the bottom would be higher than that at the top, and the wave going up the pile would be in compression. Similarly, when we have skin friction resistance, the skin friction resistance gets activated at its location, and depending on its location, it shows up in time at the pile top, and it tends to, the soil resistance being a compression against the movement of the pile, it will tend to slow down the movement of the pile, therefore reducing velocity and increasing the force. So that's why we see the separation in the body of the pile in the time history between force and velocity, indicating skin friction. Since we can test the pile during initial driving and get that information, we can also test it during restrike to evaluate the time effect on the soil resistance in both skin friction and end bearing effects. The data can be analyzed in closed form solution for immediate results between hammer blows on site, but it can also be analyzed using automatic or interactive signal matching techniques. The result of which is to the refinement of the static load bearing capacity of the pile, and also the separation between skin friction and end bearing, and furthermore, the distribution of the skin friction along the pile length. Given all of that information, then we can simulate the static load test. So this is a simulated static load test from the dynamic measurement. So the dynamic measurement and the signal matching produce that simulated static load test of pile top load versus movement that can be compared to the actual full-scale dynamic static load test and dynamic load test comparisons. There have been many cases in the literature that compare these two results, and if the data quality is good, the analysis is proper, one can expect to have excellent correlation, as has been shown in this ASCE paper publication. So this type of testing is typically implemented by a test pile program, the purpose of which is to come up with production pile length and production pile driving criteria, but also to check the engineer's design assumptions and the contractor's equipment, means, and methods for the project. So the process of establishing pile driving criteria starts with a dynamic load test, followed by the analysis of the data, and then the refinement of the wave equation analysis before a pile driving criteria is issued for the inspector to apply on site for the acceptance of the pile. So therefore, engineering, construction, testing, and inspection all work together as a unit for a successful project using this procedure. The following are a few cases that show the use of it. This is an expressway project in Central Florida. It involved about 1,000 H piles, HP 14 by 89. The original design was to have a pile load bearing capacity of 182 tons per pile. At the beginning of the test pile program, it was quickly realized that the piles actually have more capacity than had been originally anticipated, originally calculated, which resulted in increasing the load-bearing capacity to 254 tons, which allowed the reduction of the number of piles from 20 to 14 piles per footing, resulting in a saving of about $1 million for the project. There's another project at the Orlando International Airport for the transit system guideway. The original project information provided to the bidders showed 120-foot long anticipated length pile, 24-inch diameter pipe piles having a capacity of 100 tons. However, the design build team that won the project decided to use a smaller pile, a shorter pile, and higher load by utilizing dynamic and static load testing. And so various locations along the alignment of the project were picked to perform test pile program that included the driving of piles and dynamically testing them. For example, at this bent location, the required capacity was 484 kips. The pile was initially driven, having a capacity of 300 kips. 10-day restrike, 500 kips. So it was quickly realized that there is setup to be gained here, and the design build team utilized that setup effect at the various locations to optimize the use of the piles and utilize the dynamic and static load test to verify the results. This all had been published again in an ASCE paper that can be referenced. using both the end of drive capacity and skin friction and the restrike, short-term restrike capacity and skin friction. One can then extrapolate that to calculate and to simulate a static load test, load versus movement, incorporating anticipated setup in the future. And this time it was extrapolated up to the time of the static load test, which was about 2 weeks or so after initial pile driving. So this is a Class A prediction of what would be expected beforehand. The static load test was actually performed, but had to be stopped at the level where they reached the limit of the loading frame. And when we superimpose that, it fits very nicely with the anticipated result, as would have gotten from the end of drive and the restrike result. Two static load tests were performed to verify the results. And at the end, they ended up using piles that are much shorter than originally anticipated to higher loads for the foundation and to finish the project, which included about 300 piles. 30 dynamic testing were performed on 30 piles, 2 static load tests, and the driving criteria incorporated setup. And the piles were much shorter than 120 feet, only 72 foot on average, resulting in a saving of $1 million for the project. This is a more substantial project where the highway department decided to do a pre-construction test pile program that included the driving of 4 different pile types: 24-inch pipe pile, H pile, 24-inch pre-stressed concrete pile, and 30-inch pre-stressed concrete pile. So 4 different pile types at 3 different locations, 3 piles each of each type at the 3 locations. So quite an extensive program. The test pile program cost $650,000. The soil borings cost $750,000. So the idea was for the highway department to issue a report to the bidders of the project with such information to hopefully help in optimizing the use of the design for the design build team, and therefore make the project less expensive and the bid less than would otherwise be as normal. So the test pile program was based on strictly dynamic load testing, no static load testing, that included the various pile types. These are results, for example, from the steel pipe piles that show the end of drive data and the restrike data, indicating tremendous amount of setup effects. So the end of drive was 341 kips, and the restrike was 900 kips. A tremendous amount of setup information that is very valuable for the designer to know ahead of time before bidding. So the bid went out for the project at $50 million to rebuild that bridge. So during the construction of the actual project then, that included about 1,150 piles, there were an anticipated tip based on the findings of the pre-construction test pile program that the contractor design build utilized, and they used an ultimate load bearing capacity of 450 tons on the piles, 24-inch piles indicated. To summarize what the findings of all of that, the pre-test pile program information was used, and additional testing was performed during the production process at various locations as planned and also as needed. So if a pile did not take up capacity, then setup was utilized by testing and restrike. As a result of all of that, including the cost of the test pile program and so on, the anticipated bid was $130 million, and then the saving was $20 million for the project. Some projects actually decide to use not test pile program procedure, but to actually do 100% testing. So 100% testing have the benefits of optimizing construction efficiency and economy and increasing engineering reliability. So obviously contractors like the first, which is to optimize the construction efficiency and economy, and engineers like the engineering reliability increase, which means that now they can use a lower factor of safety or a higher fee factor in the LRFD design process. Some projects actually combine both a test pile program and 100% dynamic testing. This is such a project that was recently finished for a bridge where the design build team decided to employ both. It's a long bridge, 3,300 feet, consisting of 42 bents of piles, each bent having 5 piles in it. They drove initially 12 probe piles around the alignment of the bridge with dynamic testing, used the results to design the foundation, and then dynamically test 100% of the pile foundation for the project. In many situations, there were consistency and uniformity in the depth at which the bearing layer was done. As we see in this picture, most of the piles were driven to about the same depth. Well, not always. Sometimes the variability was very high, something that was overcome with the dynamic testing, so the pile can be driven to bearing as indicated by testing and measurements rather than just a simple blow count. As a result of this process on this particular project, the savings were $445,000 on the project, which constitutes about 17% savings of the foundation cost. So just remember, all of this is dynamic testing, and it's nothing but the wave. So just remember, it's all in the wave. With that, I thank you, and I wish you happy pile driving and testing.
Well, thank you, Mohamad. I think you deserve the prize for all the presentations that have been given at It's Money webinars. You definitely put in an awful lot of information, and I really appreciate the efforts that you made to give a very interesting presentation.